So we have one more theorem to go in this section, and with that I'll have some examples and couple of problems before we complete this chapter. So the last theorem in this section is this: let K and H be normal subgroups of G, then G such that K is a subgroup of normal subgroup of H, normal subgroup of G, then the factor group G over H is isomorphic to the factor group of G over K over G or H over K. H over K. Just after this theorem, I'm going to give you an example that demonstrates the second theorem and the third theorem. So it's going to be very clear after this. So in order to show that these two are isomorphic, the approach we are going to do is we are going to define a map from G to G over K, K over K, and with a kernel, and show with a kernel H. So we are going to define an onto map, and that is going to be a homomorphism with a kernel H. Then with the first theorem, this is going to be isomorphic. So the definition of phi is going to be like this: define phi of, take an element from G is equal to the element of this factor group. See, if you take a factor group, let us take G over H. The element of this will be AH, where A belongs to G and this. So this is going to be an element of this, that is GK times this H, that is H over K. So that is a definition of this map. Now clearly this is an onto function, onto map, because for every element here, every element of this group is of the form GK K over H. This is the general form of any element, of this group, and this is actually mapped to G. So this is an onto map. So clearly phi is onto. You need to show that this is a homomorphism. So what we do is phi is also a group homomorphism, because for every G1, G2 in G, phi of G1, G2 is equal to, by the definition it is going to be G1 times G2 of K H over K. And this is G1K times G2K times H over K. And that is equal to G1K H over K times G2K H over K. And that is equal to phi of G1 times phi of G2. And that implies phi is a onto homomorphism. So from the first theorem, we have of homomorphism with the kernel H. Why it is H? What is the kernel of this? Kernel of phi is equal to G belongs to G such that phi of G is equal to H over K. And that is nothing but H. This is the identity of this group. So that means the G over the kernel is isomorphic to the phi of G. The phi of G is nothing but G over K over H over K because it is onto. And that implies G over H is isomorphic to G over K over H over K. Another way of looking at this theorem is in terms of canonical homomorphism. So we have a map from G to G over H. A canonical homomorphism is, let's call it as gamma H, which is defined by of G is equal to GH. Similarly, we have another map from G to G over K. Now, let us take a normal subgroup of this, which is K over H over K. So, G over K over H over K, we can define another canonical homomorphism Y of H K. Then these two are isomorphic, and that's what the theorem says. So this is the isomorphism we are talking about, either this way or this way. So there is another way of looking at in terms of canonical homomorphisms. Now let us do some examples to show the theorems 2 and 3. So the theorem 2 says that if H is a subgroup of G and N is normal in G, then Hn over N is isomorphic to H over H intersection N. And the theorem 2 says that if H and K are normal in G such that K is a subgroup of H is a subgroup of G, then G over H is isomorphic to G over K over H over K. So we will do an example, a computational example to show these two theorems. So first let us take G is equal to our Z24, and that is 0, 23. And H is a subgroup generated by 4, and that is 0, 4, 8, 12, 16, 20. And this has got how many elements? This is 24 elements. This is 1, 2, 3, 4, 5, 6 elements. And N is equal to, it's a subgroup generated by 6, and that should have 4 elements. And the smallest subgroup, that is 8, should have 3 elements. Now let us compute one by one. Hn is going to be 0, 2, 4, 6, 8, 12, 14, 16, 18, 20, 22. There are 12 elements. You can compute this. The definition of this is actually H plus N. H belongs to H, and N belongs to N. The operation here is plus. Okay? And H intersection N is going to be 0 and 12. There are 2. So we'll find Hn over N. N has got 4 elements. Hn has got 12 elements. So this should have 3 elements. And that is N, N plus 2, N plus 4. And if you want to find those elements, you can expand N plus 2, and yeah, this is fine. This is okay. Now we'll find H over H intersection N. H is 6 elements. This is 2 elements. So this will have H intersection N, H intersection N plus 4, H intersection N plus 8. So this has got 3 elements, and this also 3 elements, and these 2 are isomorphic. Now we will compute the factor groups in theorem. This is theorem 3, by the way. 3. G over H is equal to, G is 24 elements, H is 6 elements, so G over H will have 4 elements, and that is H, H plus 1, H plus 2, H plus 3. Similarly, G over K, K has got 3 elements, so this will have 8 elements, K, K plus 1 dash dash, K plus 7, and H over K, H has got 6, K 3, so it should have 2 elements, and that is K, K plus 4. Okay. Now this has got 8 elements and this has got 2 elements. So G over K over H over K will have 4 elements, and that is H over K plus K plus 1 H over K plus K plus 2 H over K plus K plus 3. So this has got 1, 2, 3, 4. This has got 1, 2, 3, 4. So G over H is isomorphic to G over K over H over K. And that is theorem 3. Now let us do a very simple problem. Let H is a subgroup of G and N is a normal subgroup of G. Then H intersection N is normal in H. This is actually, we already assumed that this is true in theorem 2, but we are going to show, because we already did Hn, the factor group of Hn over N is isomorphic to H over H intersection N. If we need to define this one, this has to be a normal subgroup of H. But we assumed that we are going to show this is actually true. So how do you show that this a subgroup is a subset is a subgroup is normal in a group? So what we'll do is let X belongs to H intersection N and H belongs to H. Then we need to show that H inverse belongs to H intersection N. This is what we want to show. See, this implies X belongs to H intersection N implies X belongs to H and X belongs to N. So, and H belongs to H. This is also there. So what we'll do is, we'll take these two together. So H inverse belongs to H because X is from H, H is also from H, so this is actually in H. Now we'll take the other part. X inverse belongs to N because N is normal in G. So N is normal in G, right? See, this X is actually in H and N. So this is an element in N. This is an element in G. So because N is normal, this belongs to N. So that implies Hx N inverse belongs to H and N. And that implies H intersection N is normal in H. It's a very simple problem and we already assumed it, but these are the steps to prove that it is normal. So let us do another very simple problem. So let H, K, L are normal subgroups of G such that H is a subgroup of K is a subgroup of L then K over H and L over H are normal in G over H. It's a very simple problem, but I thought let us do this. So the way we are going to show this one is H is a normal subgroup of G, so we can always define the canonical isomorphism from canonical homomorphism from G to G over H. So since K and L are normal in G, so is gamma of L, gamma of K and gamma of L in G over H. Meaning gamma of K is normal in G over H, gamma of L is normal in G over H. But gamma of K is nothing but K over H. And gamma of L is nothing but L over H. And that implies K over H and L over H are normal in G over H. So let us do one more simple problem before we complete this chapter. That is, it's also very, very simple. Let K and L be normal subgroups of G such that the intersection of K and L is equal to the identity of G and K join L is equal to G. Then G over K is isomorphic to L and G over L is isomorphic to K. These two are normal subgroups. So since K and L are normal, K join N is equal to Kn is equal to KL equal to LK. Right? Because L and K are normal. So G over L is equal to KL over L, and with the second theorem it is actually isomorphic to, this is, you can say isomorphic to K over K intersection L, and that is equal to K over E, because the intersection of L and K is E, and that is equal to K. Similarly, G over K is equal to LK by L, LK by K, and that is isomorphic to L by L intersection K, and that is equal to L over, that's equal to